justice to the full concept. And then to pretty quickly specialize to those objects we are interested in and to say more about them. Okay, as a very rough intuition, but that's actually a good intuition, a topos is a category which is structurally similar to the category of sets and functions. So in a suitable sense you can think of objects in a topos as generalized sets. They behave like sets in many ways. We'll see in which ways I mean. And the arrows behave like functions. Of course, I can have lots of extra structures on these objects, on these arrows, but for now let's just get the basic things in place. So one of the very first things is that there's no agreement with right pluralists of this word. So it's topos. Some people say toposes, and other people say topoi. And I was being told by a native speaker, Greek native speaker, that the modern pronunciation would be topi. We would write it this way, but you would not pronounce it topoi, which sounds very ancient to a Greek person. But I think ancient words are good things. So, yeah.
And I think it's an SGA4 version uses just topos as the plural.
Yeah, that's because he took it from Greek into French, and my French is so limited that I won't make big statements, but I think in French you would form the plural just as topos written the same way. So if you prefer this, well, this could be even more confusing, I guess. But it's true, you know? And by the way, SGA, many people have heard this, I guess, but it seems that Grothendieck was still alive, very secluded. He just objected to this re-editing and republishing of SGA, so the website has shut down a few days ago, which is kind of a shame. But of course, Grothendieck was the person who came up with the idea for topos. First, this was early 60s, and this was in algebraic geometry as a very general notion of space, because there you run into situations where you want to talk about spaces which don't have enough points or difficult to handle in other ways, and then you can look at sheaves over such structures, and those form topos. The form of topos that we were using mostly actually is a bit younger, as the form found by Bill Lavia and Miles Tierney in 1967, I think. So this is what's called an elementary topos. But there are lots of different aspects to it, and we'll just touch upon a few things. Okay, I'll say topoi, and you can just pick the convention you like. Let's first talk about sets, because we want to do certain things with the objects, we want to be able to do certain things with the objects in a topos that you can do with sets. So the first thing, if you have a set, you want to talk about subsets. And actually two equivalent ways of doing that, and I'll show you what I mean. So the first is, so for now we talk about sets. A subset S of some set X, can be described either simply as an inclusion even two indices, so I don't do this. This is one way, or by so-called characteristic function. I mean here? Well, it's a function chi s. This actually gets an index because I need it from x into 1. So just this two element set, and the idea of course is I take a little x here and send it to 1 if x is in S and 0 if that's not the case. Okay, this is pretty simple, and of course these two things are related, and we'll now write down how they're related. Just a one-element set. This is writing this as one is a typical thing in category theory, and well, I presume a little bit of category theory, obviously. So this is, as you know, the terminal object. Sets where here I mean the category sets and functions. The terminal object of course just means from any other set I have a unique arrow function going into this, and that's clear. If I have any set, I send all the elements to this one. Okay. So this, and let true be the following arrow. Goes from 1 into this two element set. And obviously can just pick one of the two elements given by true of star. The only element in 1 is element 1 here. Then following diagram. Well, let me write down first and I'll say what it is. So this is this unique arrow sending, in this case, the subset S to this star. Here we have another arrow, which is true. And we have a third arrow, which is just the conclusion of S into X. And this diagram, and here I fill in this chi S. This diagram not only commutes, which means it doesn't matter which way I go, but it's more of a pullback diagram. So is a pullback. Okay, what does this mean? You could put other sets here to still have a commuting diagram. You could put some subset of S there. All elements go to star, this goes to 1. Let's go this way, well, via the inclusion I, this goes to X, and via chi S, this also goes to 1. You would still have a commuting diagram if you would put a subset of S there. The fact that it's a pullback diagram guarantees intuitively, if you disassemble the definition, that this is the biggest set you can put here. You cannot put anything bigger here because then you would not have commuting diagram anymore. Okay. I dotted this one because typically later we'll have a situation where these three arrows are given, and then we'll have just one choice for this arrow to make a pullback diagram. So this is why this is a bit different from the other arrows. Okay, that's pretty straightforward, but we already see that it becomes much more categorical in the sense that we now talk about objects and arrows. We have a nice diagram and a categorical notion like a pullback. I indicated by this little hook here that I is a monic. Of course, this is also a monic, which for functions just means they are injective functions. And the inclusion obviously is an injective function. This trivially also is. Okay, but this is something very interesting already. It means that every subset inclusion is the pullback of this arrow true. So this arrow true plays a very special role. You get every subset inclusion as the pullback of this arrow. So let's write this down. Every subset inclusion is and well, as I said, I presuppose a little bit of category theory, but if you're not too familiar with that, this is a pullback diagram, and I say this arrow is a pullback of this one if I intuitively pull it back against the direction of these two other arrows. So this is where this expression comes from. This is what it means. Okay. So, categorically minded people already see something. I could put some object in my category of sets, let's say some S prime here, which is isomorphic to S. It just means for sets, a set which is an adjective correspondence with S. I could also find, let's say we have an iso phi between them, then of course I can get an injective arrow here, and I'll still get pullback diagram and all these things. It's just to say that, of course, in categorical terms, you will fix this object here, this pullback object, up to isomorphism. You can't do more, but that's fine. When I'm thinking about sets, I usually take the liberty to think of this as an actual subset of this one. Categorically speaking, a subset is something more general. It's just it's actually an equivalence class of these monics, these injective functions, because this S prime also counts as a subset of X categorically. Usually I'll just take the liberty and think of an actual subset because it's convenient. But categorically speaking, a subset of X would be a whole equivalence class of these inclusions. So whether I pick S prime or S anything other, isomorphic doesn't matter. Okay. There is a logical reading to this. In particular to this chi-S. This chi-S can be seen as asking for every little x in X, well, does it lie in S or not? If it lies in S, I assign them 1, which I can also read as true. And if it's not in S, I can read this 0 here as false. So chi-S gives us the answers to all these questions, to the little x, the elements of X lie in S or not. There's nothing very deep going on here, but we already see that we could interpret this two-element set as a set of truth values. We could read this as false true, and we'll use this later on. Okay. Now, truth values here further. Well, I'm not surprised that I have two truth values. This is exactly as I have in Boolean logic. And this, I won't say too much on these logical aspects, I just indicate things. We'll see this in more detail later on. But the fact is that, of course, category sets or sets and functions itself is a topos. And each topos comes with an internal logic. And this internal logic is closely related to these, well, just to these aspects of sets and sub-objects. And here we have the natural kind of question is, does an element lie in a set or not? They're just two options. And this is why the internal logic of sets, not surprisingly, will be Boolean logic, two-valued Boolean logic. And we'll see in more detail how this works in general. And maybe one should also say at this point, though this is not a topos statement, but there is a close link between Boolean logic and the use of sets, as you know, via Stone's theorem. Every Boolean algebra shows up as global subsets of a suitable space. Okay. But now I want to generalize this. This almost looks categorical. Well, it is categorical, but I want to generalize beyond the case of sets. I want to talk about well, I won't say subset, let's call it sub-objects of objects in a way very similar to what I can do in sets. In order to write it down this way, we used two categorical notions. One was the terminal object, and the other was pullbacks. So we should have structures like these in our category to be able to generalize from this situation. And both the terminal object and the pullback are examples of finite limits. So it's another thing that you probably know. So let's write this down. Terminal object. This means they are limits of, well, limits of a functor j into, well, in our case, sets where j is finite. Explicit for terminal object, we just have the empty diagram. Well, the diagram is just the, well, it is, yeah, the diagram is just such a functor. So there's nothing interesting happening here. The pullback corresponds to, well, so J is the empty functor. Let's say. While the pullback we have, for the pullback we have J is just diagrams of this form. I should not say J is the empty functor. The functor is, let's call this F. So, of course, J is the category, which is the domain of the functor, but it is the empty category in that case. So, here F is, and J looks like this. So, why is that? pullback, you usually start from this situation. You have three objects, you have two arrows going to the object in the middle. And this is one of these codes. So we should have finite limits in our category, and then there's a theorem. You actually just need these two things, and you'll have all finite limits. So something can prove with a bit of work. Category C. Pullbacks and the terminal object. Once I assume I have a category of finite limits, of course this implies that I have an object and pullback. I can generalize from this picture, so I'll not wipe this out, I'll just generalize this. And tell you what a so-called sub-object classifier is. Definition. This is actually a pretty complicated concept, so it's not so easy to see what it does, but the analogy is very strong with what we do in sets, so it's good that we have this diagram still displayed. So it's a monic, also called true, from 1 into some object omega. So 1 is the same notation as over here, but of course it now means the terminal object in this category C, and omega is some other object. Such that every other monic S to X, and of course all this is in C, there is a unique arrow chi, which with a given monic forms a pullback square. So the diagram looks very similar to what we had over there. Maybe I should also dot this down, because this is exactly the situation where this filling in happens, if you like. So chi, we could call this chi as before. Okay, it looks just the same, but nobody says that these objects have to be sets and these arrows have to be functions. So we will see, of course, in number of examples where we don't just have sets and functions. But that's the idea very much. So you want a category which has enough structure to talk about sub-objects in the same way that you talk about subsets. Okay. Now, according to this definition, of course, this whole thing here is the sub-object classifier. In a slight abusive language, usually, as most people do, I refer to just omega as the sub-object classifier. But implicitly, there's always this arrow from the terminal object into it. Okay. There are several things to be said on this, of course. Okay. We want to get something which is analogous to a collection of all subsets, which of course we know subsets of any set form a Boolean algebra. So we want to start thinking about all sub-objects of a given object X. First thing is, if you have two different sub-objects, you can partially order them under inclusion. So write this down. So you have an idea immediately of bigger and smaller sub-objects. Of course, a sub-object, let's say S prime is smaller than subject S if S prime is a subject of S. Okay. So sub-objects sub C of subject X for search. Because that's the minimum thing you would expect, that we can sometimes talk about larger and smaller sub-objects. Okay. Now there's a technical thing happening here. The category C is called well-powered. If sub C X is a small set for every X. Objects of C. Okay. There's also something which I'm doing here, which is not necessarily what's much easier for now. I'm looking at, let's see here, a set of sub-objects. If I wanted to do things properly, I would want to talk about things internally in this category. I would want to refer to sets, because this is an external concept which is not in the topos, this is something external. I want to, because if I say a topos is like a universe of sets, I should be able to talk about sets and subsets completely internally. That is possible, but just needs a lot more work, so I will not do this. You can always change between the two perspectives, and there's actually very fruitful interplay between the two things, if you like. So, if you're interested in foundations, this may bother you. So I'm just saying here, I'm living in a meta category, in which I define my topos, and this meta category is some topos of sets. I don't have to say it's a topos, it's just it's sets and functions. As I said, you can do all these things internally and then you don't have to worry about this, but of course there are lots of interpretational and foundational issues attached to that, and I don't want to get into this discussion of foundations of mathematics. But okay.
Sorry, what was the subobject? Are the subobjects the biases?
Yes, so some objects are, I should have said this more clearly actually. This is a monic arrow, and some object is actually equivalence class of monic arrows, so we usually just say a monic is a subobject. So
but just up to isomorphism, having the same.
yes, it's up to isomorphism. This is why I say equivalence class. Yeah.
So it's got nothing to do with the subobject classifier.
It has nothing to do with the subobject classifier directly, but just as in sets, every monic is the pullback of true. And that's the point, actually.
Yeah.
True has this special property among all monics. Yeah, I should have said this more clearly. So a subobject is subobject. Well, I shouldn't actually write S. I think when I say subobject, I think of an object in the category, but actually subobject is rather this inclusion. The subobject is equivalence class of X. So let's say subject of X is an equivalence class of 1X with X. And this equivalence class aspect is something we will usually ignore and take a representative, which is convenient. Okay, all the categories we'll be looking at are well powered in this sense, but I think it should be mentioned. We get a bit more actually if we have the following thing. If f from y to x is an arrow in our category C with 5 limits, arrow in C, then we have that the pullback any monic I from S to X. Now the pullback along F is the monic let's go this I prime from this prime into no, this now goes into Y, sorry, this goes into Y. So this is the intuitive idea. If you have a function and you have here you have the subset of your codomain, you can use the function to pull back and get a subset of your domain. Something you would talk about sets, but the same thing you can do with this structure in any category with finite limits, which has a subobject classifier. And this change notation, which is not good. I goes to I prime. This defines a function. Function sub CF from a bit more space here. This goes, of course, from sub CX to sub CY. So it's just 1 plus that, and if C is well, powered by a functor, so C, of course, and this goes from C up into Z. Now, well, it should be clear. For any object, I get such a set of sub-objects, and for any function between them, I get a function between those in the opposite direction, so I have a contravariant functor. And those of you who know the so-called contravariant power set functor will see this is the exact analog of that for our situation. Again, all these things can be done internally, but I don't know, I'll talk about this probably at some point, that I would have to develop considerably more machinery to do it internally in a proper way. The keyword there are so-called power objects, which are exponentials, which we will see how Topos also has, or Topos has by definition exponentials. Okay, the last thing which relates to that is this is a representative functor. So, what does this mean? Functor is called representable if it's isomorphic to a home set functor. Following proposition. Category C with finite limits. And small onsets as a sub-object classifier, as a object classifier. If and only if there is an object omega and isomorphism theta x from sub C x okay, and this is supposed to be natural in X. And when this holds, this holds, then C is well powered. What does it say? I should have said this more clearly. Of course, you can talk about sub-objects more generally than in the situation when we have a sub-object classifier, because it just says equivalence class of 1x. But if I find an object, omega, such that every monic becomes such a pullback, or equivalently if for every sub-object I have such a characteristic arrow, as it's now called, chi s, from x into omega, so these guys here. If that's given, then I have a subobject classifier, and of course omega is this object showing up here, which I already said I would usually call the subobject classifier. Categorically, it means the functor sub Cx is representable, the representing object is omega. Interesting point here is we will see that we can understand, or basically assume that we have categories which have a subobject classifier, and then we can always think of subobjects as arrows in the category which have as their codomain this object omega. This is a very useful way of thinking about this later on. Okay, now we actually have all the pieces that we need to define what the topos is. Actually, it doesn't need much space, but it's one of those definitions which you have to unravel and play with. But the actual definition is very short. It could be made even shorter because some of the things I'm defining follow from others, but this needs a lot of work, so it wouldn't make sense to put it even more shortly. So the definition is the following. Elementary topos is a category E with the following properties. So the first thing is E has all finite limits and also co-limits. We saw already that having finite limits implies existence of terminal object and existence of pullbacks. We know you get products as finite limits. Dually, you get an initial object, co-products, and all this stuff from co-limits, push-out diagrams. So all this is there. The thing I didn't talk about much, and this is the extra machinery we would need to understand these things more internally, are exponentials. So E has exponentials. And finally, E has a subobject classifier. Okay. We already saw that a subobject classifier is the tool that allows us to generalize from this two-element set, node 1 in sets, and allows us to talk about subobjects in a way very similar to what we do in sets. And we also see more how this is related to logical aspects. What about exponentials? Well, if you have two sets, see here, x and y, you can form, let's say, y to the x. It's just a notation, it's all functions from x into y. Okay, so it's functions from x to y. But interestingly, these functions form a set. This is a set of functions. So this is another construction you can do. You can take two sets and get another set in different ways. And one of the ways is this. So function space, if you like, are also sets. That's an interesting thing. If you think about it categorically, you have a bunch of arrows, but they become an object again. This is, of course, a particular thing that you may or may not have in a category. And, well, the proper categorical analog of this are exponentials, and they're also there in every topos. So you intuitively have these function spaces. Okay. And finite limits, as I said, set include products, so you have things which are analogous to Cartesian products of sets, and colimits include coproducts. You have things which are analogous to disjoint unions of sets. All these things are there in the Topos. This is emphasizing very strongly this analogy with sets here. Okay, I think it's time for a few examples, and one example you all know, of course, is just a category of sets and functions, the Topos itself, obviously. But we want to see a few other topoi and get some idea what becomes different and how this is a generalization.
Is this definition enough to say that you have power objects? Or is
Yes.
that stronger?
No, that's not strong. That's equivalent to saying you have power objects. Power objects would be the internal way of talking about these sub-objects. So, well, let's leave this for a moment. And okay, so category of sets, as I said. Well, sets times sets. That's one thing you can look at. Sets squared is not the same because 2 is this category. 2 objects, one trivial arrow between them. While here you would have the category, if you like, just having 2 objects but no arrow between them. Okay. Some which looks different is BG. This is category of G sets, which has objects, sets with, let's say, right action by G. Of course, you could also consider left actions. This is just a choice. And arrows are so-called G equivariant functions, so functions which behave well with respect to the group actions of different sets. Very importantly, this is mostly considering set C op is where C is a small category. This is, well, the objects are functors from the opposite category of C into sets. I'm oscillating between set and sets, so I never know what's going on. So let's write sets. Sets. So you have, if you see this as a functor on C, you have a contravariant set-valued functor, and this is just traditionally called a pre-sheaf. So called pre-sheaves. And to make it precise, they're called pre-sheaves over C. Arrows are natural transformations between these functors. this closely, all these are examples of this. So this is the general thing. Just have to figure out what C is in each case. But so this is a very general thing. Finally, category sheaves of X, sheaves on a topological space, and X can then be generalized beyond the case of being already a topological space, but we won't go there for now. Sheaves over X. The other nice things, there is a nice paper, give you the reference. It's called The Guided Tour and the Topos of Graphs. So you can look at graphs, but they are actually this topos of graphs is also a pre-sheaf category. And sheaves are also pre-sheaves. That's not the best way of looking at sheaves, but in some sense this is really the paradigm that we're really interested in. Okay, well, let's look at these two for a minute, just to show how does omega look in both cases, just to get some intuitive idea what's going on there. Okay. So, let's say sets times sets. Well, it's not hard to guess. Omega is pair of sets. Of course, you have to check this, but it works out. The objects there are pairs of sets, and the terminal object, the subject classifier will become this. What is, well, the terminal object is of course, just two copies of the one element set, and our arrow true, of course, goes from 1 to omega, 1 to omega, and take this pair star 2, 1. Okay. But already in this very simple example of pairs of sets and pairs of functions between them, you have 4 truth values, because what happens in this component is independent of what happens there. So let's write this down. Truth values. So these are just this the subset. Well, I'll take one element here, one element here. So 0, 0, 0, 1. So at this point I have to say what I mean by truth values. It's simple in this situation where we're still dealing with sets, but it may happen that our objects are not sets anymore. So the idea is that a truth value is an arrow from 1 into omega. So in particular, this is a truth value, of course. The logical interpretation of this particular one, which will, we will see the truth values also have a partial order on them. This will always be the top element. And this will be interpreted as totally true. Truth values will also always have a bottom element. We'll see this in a minute. And of course in this case it's 0, 0, and this is totally false. But already in this situation you get other truth values which are somewhere in between. And also interestingly, see the process structure that you see you can't compare these two. There's not one of them bigger than the other. So this can happen. So this is maybe also something interesting to get used to. You have more truth values, they only form a partial order, not a total order in general. Okay, So what do I mean by truth values? Well, I want to do a small step into something more general, because that's also very useful. We want to talk about elements of objects in a more general setting than just sets. So if you have a set, say x, and we have an element little x in x, we can equivalently talk about the following thing. Determines a function, let's call this function, well, I would like to call it x as well. And this goes, well, from, actually goes from the terminal object into x and sends star to x. Very simple idea, but we have suddenly the ability to talk about elements in the form of arrows. And this can be generalized easily because we just have some categorical structure here, the terminal object here. So now I can talk about elements in any category which has a terminal object. So let's do this. Let's see. Catch 1. Then element of x in, this is in the objects of C is an arrow, well, let's call it, I don't know, making x also from 1 into x. Complete analogy to this, but I don't have to presuppose that x is a set or anything. So I can think of elements in terms of arrows. And when I now say I have such an object omega here, and talk about truth values, they're nothing but the elements of omega in this particular sense, the sense of arrows from a terminal object into omega. So truth values, can have that much space, so let's knock this out. Like it says again, it's an external description. I think we might want to have a break. No, I think let's have 7 minutes of break. The truth values are these arrows. So these are these arrows. Now, of course, the truth values are nothing but the sub-objects of the terminal object. By this proposition we had before. So that's also a way of thinking about it, and think about sets. The terminal object is a one-element set which has two subsets, the empty one and the set itself, two truth values. So it works there, and this generalizes in this sense. Okay, of course this is a pretty boring example. Let's quickly have a look at sets. 2, where we have this, so we suddenly get a relation between these two sets, and I don't want to say too much about it, but the point is that
So sorry, Andreas,
yeah.
set 2, is it all functors from like the 2-point category into set?
Yeah. Yeah. So it means you pick for each of the objects here, you pick one set and you pick one function. Yes,
Okay.
it's all functors.
Yeah.
All diagrams of this shape. Yeah.
Right.
Yeah. Okay. Now exercise. So object is this. That's not very surprising. And the truth values, how many truth values are there? Can everybody see this?
3.
Yeah, there are 3. They're not 4 anymore because we have a condition. So if this, well, you have one which is empty, you have one which is the whole thing. But there's only one more, because if this here is non-empty, this must be non-empty because you have a function between them. So you have one where this is empty and this is non-empty. So you have a truth value of this form, but you have no truth value of this form. This doesn't exist because there's no function from the one element set to the empty set. So this goes away, so we have 3 truth values in this topos. Okay. Good. And so we're finally in a situation where we can, well, okay, one more example, our big example, so to say. That's important. Again, this needs a proper proof. This is some work, but I want to tell you how the subobject classifier looks in such topos. So, first of all, the object 1 is constant, let me write it this way, constant star pre-chief just means to every object C in category C, you assign the one element set, and to every arrow you just assign the identity function between these one element sets. This is what I mean by the constant star pre-sheaf. And, well, the truth values are the sub-objects of this guy. And like in this case, which is of course the smallest non-trivial poset, we have to take into account certain things. We can not have something here but nothing here. Okay. And this is encoded in general in the following way. So, I wrote down the yes. Okay. So we have to define something first. I wanted to say what omega is in our case. So the thing is, we will, and this is kind of a general principle, we very often have a situation where we talk about pre-sheaves, where I define something first for a single object C in the category C, and then I glue it together. So this whole thing, this going from the local to the global, this will play a big role. The interesting objects are always the global ones. With pre-sheaves, you're very often in a situation that you can define things locally and fit them together neatly and get something global. And pre-sheaves are much less restrictive than sheaves in that respect, because you have to fulfill stronger conditions in sheaves, and this is why not every pre-sheaf is a sheaf, but the other way around is true. So I first want to say something local, so the so-called SIF on C in the objects of C is, well, it's a bunch of arrows which all go to C. Is, let's write this down correctly, is collection, let's call it sigma, of arrows domain C, such that, well, if I have some arrow F from, let's say, an object B to C, sieve, and I have another arrow G from A to B, where B is this, where F starts. Then I also have that F after G, which of course goes from A to C, is in sigma. So sieves are downward closed in this sense. If you have some element in your sieve and you have anything that you can pre-compose, the composite is also included. So a useful picture which works particularly well for pole sets, and for most of our applications C will be a pole set, is the following. You have, let's give me some space here, you have some object, this is our object C, so you have an arrow, this is our F, going there from B. Then you have other arrows going into B, with all these composites going into C, they're all contained. And likewise, something here. There is obviously a maximal sieve on every C, which contains all arrows which land in C, and there is a minimal sieve which is just empty, so no sieves. Yeah.
Are sieves related to filters?
No, not necessarily, because, well, filters, it depends on what your definition of filter is. Do you think of filter in some kind of semi-lattice at least? There's no obvious semi-lattice operation between arrows, so this is a limited analogy. Of course, the kind of closeness, downward closeness, this reminds of filters, I agree, but I think to define filters you would just need a bit more structure than this here. Okay, this picture is quite useful, and especially can imagine if we have pole sets where we actually can write them. Let's say the bigger elements are up here and the small elements are down here, then this is particularly useful to think of it as such a thing spreading out. Okay, so this is what a sieve is, and now I want to tell you how you can go from sieves on one object to sieves on another if you have an arrow between two objects. So if H goes from C to D, and sigma is sieve on C, then, well, definition sigma dot H, this is a collection of all F such that H after F is in sigma. You can check this very easily. This is a sieve on D. No, sorry, no, I'm wrong. This is a sieve on D, and this becomes a sieve on C. And this is called the pullback. I need something contravariant, actually, I should have seen this right away. Pullback of sigma along H. So this pullback is, well, it's not a categorical pullback, this is just the same word. But this gives you, from a sieve on D and such an arrow as on C, so you see obviously get something contravariant, and we can define a pre-sheaf. So the pre-sheaf, this actually, I'll write it as omega already because this will become our subject classifier. Pre-sheaf of sieves is given, well, on objects for all C clumsy, they always have brackets. So only C is the set of all sigma is set on C. And on arrows, of course, we use these pullbacks. On arrows for all F from, this was actually H, let's use the same notation we had, H from C to D, we have that omega of H is going from omega of D to omega of C, and well, just write pullback. Sigma goes to C is sigma dot H. Okay. So obviously we get a pre-sheaf this way, and it's a bit of work to check that this is the subobject classifier, but what's not so hard to see is that a global element of this, well, okay, an arrow to omega is what's it called? This is pre-sheaf speak. I just introduced that these are called elements. In pre-sheaf language, they were very often called global elements. Sometimes global sections. So an arrow is a sub-object of one, which is this constant start pre-sheaf. That's pretty easy to see. So you pick one sieve for every object C. They all fit together nicely under these pullback mappings. And then you see very easily, this is, well, I'm telling the truth here. I'm thinking of pole sets. I don't want to talk nonsense. It's definitely true if C is a pole set, but more generally we should still have, well, we still have this, so it's still true. Because I'm just saying one guy here is a subobject with one, so it's still true. It's easy to check if you have pole sets, because then you just have very few arrows in your category C, and then you see quite easily that this works. So time is running out, so I think I'll stop here. And so the thing is, the next 2 weeks there will be no lecture. I have a lot of this stuff on slides, so I'll edit this a bit.